Welcome to the last lecture, the 60th lecture of surface engineering. We have covered quite a bit, and I hope during the course of all these lectures we could arouse sufficient interest in you about surface engineering and its utility and scopes of application. But before we wind today, I thought I would review the overall scope of surface engineering again, including the scheme of classification, because classification is a way of actually addressing the entire subject domain and also take a summary look or bird's eye view so that we know exactly what is the overall scope and what are the different possibilities of application. So before we talk about surface engineering, obviously the first and foremost question is what is a surface and what are the surface dependent properties. And if you recall, we did say that for any solid, whenever we look at the external surface, the surfaces could be internal as well as external, but we are primarily by surface, what we mean essentially is an external surface. So for a three-dimensional solid, we certainly will have certain external surface or so-called solid vapor surfaces, and this is where the coordination or the surrounding atoms or ions or molecules, the species basically, the environment is going to be different. So there will be at least 1 degree of freedom for any atom located at the surface than an atom which is in the center or in the interior of the solid. So because of these at least 1 degree of freedom, there will be certain dangling bonds, and the cumulative effect of these dangling bonds give rise to what is known as surface tension per unit length or surface energy per unit area. So the origin of surface energy, as we understand, is due to the unsaturated bonds or the cumulative effect of the unsaturated bonds at the surface. And this is true for all kinds of solids, not only pure solids, not only just metallic, ceramic or polymeric solids, but even composites, aggregates or all kinds of solids. But of course, the surface energy varies depending upon the condition, the composition and prior history of the solid, and based on that we have different manifestations of surface energy. Now, to a large extent, the surface energy influences the surface dependent properties. So as I said, we define the surface in terms of its structure, the atomic or ionic or molecular aggregate that we are talking about, its composition, and there is always a possibility of little variation of the surface composition than the bulk composition, because surface is always prone to absorbing impurities from the atmosphere around. We talked about surface energy just now, which is a very important characteristic of the surface, and obviously the various forms, various types of surface dependent properties. So there are 3 major classes of surface dependent properties we have already talked about. One is the mechanical properties, namely the hardness, wear, friction, and so on and so forth. We can have properties which are of chemical nature, the corrosion properties, catalysis, oxidation, chemisorption, even various kinds of diffusional activities and so on. So primarily depend upon the composition and the chemical, the Gibbs energy or the chemical potential of the surface. Also we talk about or we are concerned with various physical properties like the adhesion, reflectivity, emissivity, for example the optical emission properties, or simply the aesthetics or the appearance of the surface and color and so on. We need to talk about surface dependent properties for various surface engineering considerations or in general engineering considerations. So surfaces are important for various engineering considerations, be it design or life prediction or assessment, or the performance properties, safety of the component, its reliability, the aesthetics, the look, appearance, the quality, the cleaning properties, environment and environmental interaction, and obviously bit of modeling exercises. Now, there are various surface engineering techniques. I mean, just randomly I have picked up a few here. We have talked about various coatings, various cladding processes, plating or deposition, then thermal and chemical treatment processes, polishing and grinding, implantation, various diffusional treatments, surface melting, surface alloying, and so on and so forth. Just picked up randomly some of these techniques. And what are the industries? Practically all. Wherever we use a solid hardware and the surface of the solid is exposed to certain uncontrolled atmosphere, that means it's not vacuum, or it's not an isothermal condition, or it's not, there is a possibility of change in temperature, pressure, moisture content, or composition of the environment surrounding the solid. In all such cases, there could be a variation of the manifestation of surface dependent properties. So, all components associated with manufacturing, exercise, automobile industry, aerospace, textile, biomedical applications, chemical and petrochemical, power and energy production devices, various defense applications, food packaging, machinery and heavy industries, mining operations, electrical and electronic devices, almost everything that one can think of. So, as we just now mentioned, we divide them into three major classes: physical, mechanical and chemical. For example, roughness, color and reflection, emissivity or emission characteristics, wettability, adsorption, adhesion, cohesion, all these properties, we club them under the physical properties. Mechanical, of course, is well known: the hardness, the friction, wear resistance, fatigue properties, even fracture, because these are surface dependent. The failures mostly initiate at the surface, though to a large extent they are bulk properties, but initiation is always at the surface. Similarly, chemical properties in terms of reflectivity, oxidation, corrosion, catalysis, particularly high temperature oxidation processes and so on. Now, how do we approach the entire or the vast field of surface engineering? And in fact, this is something it's not very easy to comprehend the entire scope in one snapshot, but that's exactly what we have tried here. So, in terms of dimension, we already classified them into possibilities where we add on additive type, we only modify, don't change the dimension, or we remove from the surface, typically like polishing, grinding. So, when we coat and deposit or clad, then we are doing addition. When we only change the microstructure and not change the composition, or not change the dimension, then we say simply modification, or when we remove, then we say removal types of processes. The type of changes associated with any surface engineering process would be primarily of two types. When we don't change the composition and change only the microstructure, appearance and various other physical attributes, we call it physical approaches. Otherwise, in vast majority of surface engineering processes, we change the composition and we call them chemical surface engineering approaches. And these physical or chemical methods can be carried out either at ambient temperature or at elevated temperature. Now, we already said that property wise we'll be worried about will be concerned with the mechanical properties, the chemical properties, and a vast range of functional properties. I mean, electrical, electronic, various types of physical properties which are of functional nature. In other words, which are not dependent on the activation based on mechanical forces or chemical interaction. So, the way we do surface engineering, for example, anything that we want to add on or introduce to the surface, modify the change surface composition, or simply bring the surface to some kind of activation or influence, these things we do in 3 or 4 possible ways. One is that we carry out the entire process through solid, so entirely a solid state processing, for example, a diffusion coating. We can do, for example, a liquid, we can immerse the substrate in a liquid medium and then carry out certain diffusional process or chemical reaction process, essentially in a liquid bath. So, it could be a conversion coating, it could be liquid carburizing or cyaniding and so on. A vast majority could be done in gaseous state, for example, gas nitriding or various gaseous processes, or in the vapor state like PVD, CVD and so on. We can also do things in the plasma state, which actually allows us to clean and as well as to coat, to deposit, to modify, allow diffusion and various processes. The substrates can be any solid. Essentially, in one single word is any solid. So, which means it can be the metals and alloys. A vast majority of our discussion concerned with metals and alloys. Could be semiconductors, could be glass, could be ceramic, polymers, even various aggregates and composites. So, can be mixtures of that, as large as even concrete, for example. So, that is why I said aggregates. The activation, the reason, the driving force where actually the changes come from could be of mechanical nature, say for example, say surface rolling or skin pass rolling or shot peening and so on, or thermal in nature. A vast majority of them are thermal in nature, all these diffusional processes. It could be chemical in nature, could be a chemical reaction, various forms of let us say anodizing or nitriding, liquid bath processes or gaseous processes, but changes happen because of the chemical reaction happening at the surface. It could be because of the various electrical forms like various forms of electrolysis or electrolysis based processes like platings and depositions and so on. It could also, we have at the end of the course, we did have a number of lectures on ion implantation, laser, plasma, laser or electron beam and so on. So, these are the sources of various surface engineering processes happening. Almost all the surface engineering processes can be broadly divided into two major categories in terms of the coating substrate interface. So, if this is the solid and if this is the coating on top of the solid. So, this interface can either be an interface whereby if I just take a line profile across and then plot the composition say of the solute element as a function of depth, we have two possibilities. One is where we have a sharp interface like this. So, this is the coating region where the composition is entirely different than the substrate region, or the other possibility could be that we can have a diffused interface like this, where the solute atom would have diffused until certain depth from the surface, and this is a function, this usually is a function of temperature or maybe some other activation. So, whether the interface solid, the substrate deposit interface is diffused or sharp, we can divide practically all kinds of surface engineering processes we have discussed so far. Now, the user would be also concerned about the investment, the cost. So, majority of the processes are of the type where the conventional ones are of the type which are low capital cost, but high running cost because of the electricity, the various chemicals and so on, or labor cost and so on. So, these are mostly the conventional processes. Whereas, you can also have various other techniques like laser based, electron beam and so on, where the capital cost is large, but the running cost is fairly low because it is mostly automated. So, these are the so called modern surface engineering processes or techniques. Coating dimension wise, I mean this is a loose classification, not a very strict or sacrosanct division. Anything which has more than a micrometer thick coating, we say thick coatings or thick films and so on, and anything less than 1 micrometer is generally said thin. So, all these PVD, CVD, sputtering, ion plating, ion implantation, all these processes are essentially thin film coating or thin coating technologies, whereas cladding or plating or carburizing, nitriding, all these are thick coating processes. There are certain hazards involved. Like any process, we have to be very careful about possibilities of certain toxic byproducts. For example, if you are dealing with hexavalent chromium or dealing with phosphine or phosgene kind of reactive gases, even chloride ions, or there could be emission of, for example, in CVD processes, you generally have a byproduct which is halide gas. So, you can't throw it open in the air. Even in various kinds of liquid bath processes or gaseous bath processes, we do deal with toxic byproducts. So one has to be careful about those things. There could be also quite a bit of large amount of solid waste generated. All these diffusional coating processes, when the pack is exhausted, it's not of use anymore, then these packs can be actually, over a period of time you tend to accumulate a lot of pack. So it is important that we try to reuse them or recharge and reuse them. Then there could be also liquid effluents, all these acids and other kinds of byproducts. So the overall objective of surface engineering, so to say, and the overall scope, I would say, is, all these techniques, starting all the way from simple hot dip coating to all the way very sophisticated ion implantation. All these surface engineering processes, all these techniques basically could be used for various surface engineering applications. They could also be useful for various repair, refurbishment and reclamation jobs. And most importantly, this is the modern approach of or the modern scope of graduating surface engineering to the wider scope of application, which is essentially additive manufacturing. So this additive manufacturing, as I said, is nothing but it essentially is a larger version or a modified version of cladding. So you actually develop layer by layer and eventually develop a 3D product, and hence it's called 3D printing or nothing but additive manufacturing. So the overall scope, let's be, this is something I'm just repeating, which probably was part of one of the earlier lectures, very early lectures. So this we have already discussed, no? The modification, which is only changing the surface microstructure or composition without change in dimension. Or it can be removal based, where we do cleaning, polishing, grinding and so on. Or we do addition, which could be through the chemical method, through physical method or electrochemical method. So more or less all these, as you realize, all of these can be actually a physical type or chemical type, where we are not changing the composition or where we are changing the composition. So when we are doing the modification, so let's say all these altogether, I had these altogether from 1, 2, 3, 4, likewise. We kept on making various forms of changes, and then all these put together, we have identified some 15 different variants of surface engineering approaches, and they all essentially address the same philosophy, tailor the surface microstructure and or composition. So in terms of dimensional changes, where surface dimension is not changed but only we modify, as I said, we can change only the microstructure or composition, and these are the different methods. And if we go deeper, then these are the techniques we have discussed in various times. Anything starting from annealing, rapid thermal annealing, surface hardening, induction hardening, laser hardening, or any other hardening process. So this is basically a thermal process. All these are essentially a thermally activated process. So where we, so essentially is a function of temperature and time, and essentially we change the atomic aggregate on the surface or the thin films, so that certain properties, be it functional or say conductivity or maybe strength and so on, can be tailored. There could be also processes which are mechanically activated. So you essentially hit the surface with stream of hard spheres, or allow ultrasonic wave to hit the surface and create a shock wave at very high frequency for a very short duration, but creating a certain force pulses onto the surface, so that the surface undergoes very thin layer of deformation, and in the process create a residual compressive stress on the surface. This could be also through skin pulse rolling or simply hammering and so on and so forth. Then these three, the groups of 3, 4 and 5, here we are changing composition. So these two are only change in microstructure, and here we are changing the composition as well. And how are we changing? Either by thermally activated diffusion. So these processes are a function of temperature. So temperature determines what will be the depth of penetration. These two, plasma ion implantation and ion beam implantation, they are basically through, these are ballistic processes, whereas plasma ion implantation is also dependent on temperature. So we modify the surface composition and hence certain properties dependent on surface. There are vast majority of chemical reaction based modification where we don't necessarily change the surface dimension significantly, though there could always be a little bit of changes, or certain surface ripples can be formed because of surface tension forces. But the whole process is dependent on chemical reaction or chemical changes, say anything starting from anodizing to various kinds of conversion coatings and so on. We need to clean the surface or remove, so we can do anything like say rubbing, polishing, buffing, scuffing, chiseling, heavy, or when we here the amount of material removal is thin or small, and here the material removal is large. So we can think of grinding, polishing, or machining, turning, and so on. Buffing is not quite correct because generally the material removal is very small here. We can also remove materials and clean the surface or make it truly polished by way of electrochemical means, where basically the dissolution from the anode will remove ions selectively and in a controlled manner. So it will remove the surface asperities and eventually make the surface more flat and less rough. It can be through electrodischarge machining. This is not for surface cleaning or polishing, but this is for pure machining operations. One can do plasma cleaning or plasma etching, or even use an ion beam for etching and cleaning. Even say, for example, use sputtering. That's also one way of cleaning the surface. When you reverse the polarity, you actually eject atoms from the surface, and that's how you clean the surface, by sputter cleaning. You can do dip cleaning or degreasing in a chemical bath for large components. You can do chemical polishing or dissolution, where you actually may have a jet incident onto the surface. So if this is the solid surface and here is the nozzle, and from the nozzle you throw a jet and you move the jet up and down or vary the angle of incidence, and then you can clean the surface. You can do etching, where essentially you will have certain chemical reagent and you will put the sample into the bath for a certain period of time and you remove. But remember, this etching can be chemical like this. It can be also through ion or through heat tinting, by simply heating or giving certain preferential chemical attack onto the surface. So all possibilities exist. In the addition processes, we actually can do various kinds of chemical, physical, and electrochemical methods, apply them. For example, galvanizing, hot dip coating, lacquering, and painting. So this is something which we haven't discussed much in the course, but is nevertheless very, very important for anything from a large wall of a building to very sophisticated electronic device, or even decorative pieces. So you basically may apply a transparent or translucent molecular coating, so that the surface of the metal or the semiconductor does not get exposed to atmosphere directly. You can also do roll bonding, so you actually can have multiple foils and then let it pass through the roll, and then eventually what comes out will be thinner than this, but in the process you actually make them bond well within this thickness. You can do pack rolling, you can do diffusion bonding, where you have, by diffusion bonding what you mean is you actually have only two foils or two plates, and you apply very heavy pressure and expose to a certain temperature, so that this interface allows interdiffusion and forms a fairly strong bond. You can do deposition in the form of chemical vapor deposition or electrochemical vapor deposition or plasma assisted deposition processes. So, when you change the composition or you actually create a surface with a different or a coating with a different composition than the substrate, you call it chemical vapor deposition processes. Otherwise, you can also do change the composition, but when a chemical reaction takes place in the atmosphere in the vapor state and then get deposited onto the surface, you call it CVD processes. But in PVD, of course, everything comes from the vapor state, but there is no change in composition between the target from which this vapor come and the coating which eventually forms onto the surface. So, in CVD, you have a chemical reaction preceding the deposition or at the surface accompanying the deposition, and hence the deposit has a different composition than the precursor. But in PVD, you have the same composition as the target. You have various forms of spray processes, thermal spray or plasma spray or deposition. Also various high velocity processes like HVF or cold spray. Similarly, you can have processes like sputtering, which is through one form of PVD, but under the influence of certain potential difference, where you direct certain agencies to actually scoop out atoms from the target, and then those atoms are deposited onto the substrate. So, unlike PVD, the thermal activation is not the key here. It's basically those ions, particularly argon ions, which actually scoop out atoms from the surface and then deposit elsewhere. So, that's the process. You can also, in the process, you can have multiple targets and make them react in the vapor state and deposit, somewhat very similar to CVD, but the difference being that what you plate, what you deposit actually is because of surface reaction happening onto the surface. We can have ion plating depositions, ion assisted deposition. You can have plasma electrolytic oxidation. So, you take a substrate and then you allow selective oxidation from the surface, so that the metallic grains here, these metallic grains here actually get selectively oxidized, and this oxide and the metallic substrate below are fairly compatible. So, there is no immediate decohesion expected or anticipated. Normally, when you deposit by, let's say, thermal spray or plasma spray, an oxide layer on top, a thick coating of oxide layer, compositionally, structurally, they are so different than the substrate, this interface is always a question, always a suspect. Whereas, when you do oxidation of the surface and allow oxides to grow like this from the bottom, then the compatibility is much better. One can do electrodeposition or plating, or you can even do co-deposition. So, you can, for example, create a surface with an alloyed layer by way of depositing A and B either simultaneously, or most often they are done sequentially. So, you have a very thin layer of A and then very thin layer of B, or you pulse in such high frequency that in the process you do not necessarily create one layer of A and one layer of B. You actually, within the layer itself, you will have A, B, so on, and because of high surface diffusivity, they tend to intermix and form an alloyed coating onto the surface. You can also do electroless deposition or electroless plating, where the whole process is essentially because of certain catalytic effect. So, if you have a bath and if you dip a particular, so without application of any potential difference, so there is no completed circuit, there is no electrically closed circuit, but yet when you dip certain metal, because of the autocatalytic effect, immediately the ions which are available in the bath will have a tendency to deposit onto this and then form a coating. So, that is electroless coating. So, this is the overall scope of the entire surface engineering course that we have discussed. Now, I must tell you that you have to I must admit that there are multiple textbooks available, but there is no single textbook as on date which can cover the entire scope of surface engineering that we have discussed in this course. So, you have to refer to various sources, various resources, including the certain good literature available in the internet. But I would strongly advise you to rely more upon the reviewed resources, including technical papers published in the journals, but otherwise textbooks or reference books, handbooks, even internet sources. This could be very good material for you for your self-study. And always, whenever you face any difficulty, you're free to write to me an email, or we probably soon will have an open discussion session, and there you can raise your questions. But please send your questions beforehand so that I have a short and composed reply ready for you. But overall, I would end up saying that any solid, any hardware, primarily if it's a solid substrate, and is in contact with the atmosphere, either at room temperature or elevated temperature, or is undergoing certain interaction which is of mechanical origin or thermal origin or chemical origin, or there are various forms of activations possible. So under such influences, the failure or degradation of the component is most likely to happen from the surface. So how do you protect the surface, and in the process the entire component, the bulk? That's all about surface engineering. So again, approaches are very different, and what is important is that you understand the philosophy, you understand the mechanism, you understand the driving force for certain processes, why they are happening, and also understand the various forms of surface dependent properties and the way they can be improved upon or they can be safeguarded. And that's all which is included in surface engineering. So I wish you learned reasonably well, and I could make you interested in the subject, and hopefully you will be able to this knowledge in your profession, and certainly serve the society in a very, very effective manner. So thank you very much and wish you all the very best.